Greetings once again to Bob's School for Shader Hackers. Today is going to be Lesson 6, the Prime Directive. This is where we're going to talk about the actual formula, the actual math used to do stereoscopic fixes. This is as NVIDIA has defined it, which, of course, since we're using the NVIDIA driver, is the only one that matters for our purposes. I think we have a fairly good background and understanding for how to disable effects. And we actually have enough understanding of 3D now to be able to talk about the prime directive and how stereoscopic fixes actually would work. So today will be the first time that we actually start looking at how to fix effects as opposed to merely disabling them. Not to discount disabling them. A lot of times that's the most time effective way to get things done. So naturally, of course, when we are trying to fix a game, we'd rather fix the shaders than disable them. But there's always a time cost involved in actually fixing them, and disabling them is almost always quick and easy. So it's always a trade-off. And as a general idea, we probably wouldn't fix any of the effects in the ball beyond just one or two of them, because the game actually works pretty well with them disabled. So the lava effect that we're going to look at today, for example, we're going to go ahead and fix it because it's easy and it makes a good example. But and generally speaking, we probably wouldn't fix that actual effect because disabling the one layer like we did last time actually makes the effect completely fine. And makes the game completely playable. So there's not a high value in spending any of our time fixing something that has such a small minor effect on the game. So in general, I'd sort of recommend that whenever you're trying to fix something, consider how valuable is that particular effect and whether it's actually worth your time. So we're going to use the ball again as our example, and we're going to fix the lava in there. The primary reason to do that is because there's already stereo code there, and we can take a look at that, and that'll actually be a little bit more clear as we step through some of that particular code. So let's go ahead and get cracking. We're going to go ahead and take a look at the ball and get a glimpse of the 3D formula. When we last looked at the ball, we actually went ahead and fixed the lava effect by disabling one layer of the lava, which was the edges of the wave lapping effect, and that actually made it a quite functional fix. Now we're going to go back in and take a look because we stumbled across that interesting tidbit about the NVIDIA stereo flag that's in there, which actually makes sense because this is an Unreal Engine game, and the Unreal Engine has direct support for 3D vision. It's not clear what the state of that support is, but anyway, the code definitely is set up with that in mind. When we looked at it, it didn't seem like it was actually functional, but it seems fairly likely that we can actually make that work using that particular formula. Now, it's also interesting that that formula is in fact actually the same thing that I'm calling the prime directive. It's the 3 or 4 lines of code that actually do the stereo correction. So as a first glance at this, let's just go ahead and jump into the ball and into that shader and take a look at that actual effect and that actual formula to see how it's applied in this particular shader. So I'm going back into the ball to refresh our memory on what it looks like. This is in 3D. Everything seems good. The shader's been loaded, and if I disable the our fix, then we get that crazy edge effect and also haloing around the gun. So that's definitely part of how that's actually working. If I disable the effect altogether, we get our empty bed, which is no good. So anyway, our fix actually looks good and seems to be functional. So I'm going to go ahead and switch back out, and we can take a look at the actual code. So the code is here. Happen to know it's on the top of the list there. Okay, lava effect. This is our guy. So this is us doing our stuff here. Here's the code that we actually noticed before, and it's this C3 constant. C3 constant is actually the NVIDIA stereo enabled flag for this particular code. Now it seems clear that that always comes in as 0. It's not enabled. But even when we forced it to be enabled, we actually didn't get any effect, probably because this S1 sampler is actually not initialized properly. But it's always hard to say. Now, I know from experimenting on this code that actually I can get this to work by using the Helix sampler, which we'll do in just a second. But here's your first glance at the prime directive. The actual prime directive is these 3 lines of code. So the actual premise is that it loads stereo values into the R1 register and then uses them to actually do the math on the actual location in order to actually move a stereo fix. Now in this case, the location is the v1. The v1 comes in as the parameter we saw before, which is the x, y, w. W and z are related from the text coordinate 5, which actually comes from the vertex shader. So that is the position of that particular shader effect and where that texture is supposed to be painted. And so if we move this v1 value left and right, we can actually make the stereo effect work or not work as it may be. So since this code is not working at all, then that's why the bug happens. Is because we need something like this in order to fix that glitch in that texture. So that's the basic idea behind this formula. We just move these input vertices into the right spot so that they work correctly in stereo. And it's as simple as those 3 lines of code. And you'll see this over and over again as we fix different games. This is the prime directive. Okay, so given that that's the idea behind it, let's go ahead and just do a quick fix on this thing to make it actually show you how that actually can work correctly. Right now it's broken, but we can make it work without too much trouble. So what I'm going to do is I'm going to revert this code because we have too much stuff in here now. We've got on-off mechanisms for the different pieces, different keys and so forth, and after a while things get a little too confusing. So I'm going to go ahead and go back to the original version, which is still in our dumps folder in the single shaders, pixel shader, and it's 969FF, which is the right one. Here's our code. I'm just going to go ahead and copy and paste this code. If you care about your comments and all of the pieces that are in here, you should save them, of course. Since I've already got them saved, I'm just going to go ahead and select all the code and replace it. So now we're back to the original shader with no changes other than a comment at the top. So now back in the game itself, I'm going to go ahead and reload that shader to make sure that it works. And then it assembles and nothing else strange happens. Always good to double check. So we get our effect. Keys no longer work, so we are actually back in operation here. Now one thing I wanted to show you is how does this look in 2D? So in 2D, the actual effect is supposed to be like it is now. Waves lapping at the shore, maybe a little haloing at the edge of the rock wall there to show that the lava is making that part hot. Not exactly sure what that effect is supposed to be showing us. It definitely has a fast edge on there, but it's only showing that one piece. It's not a particularly impressive effect, and to be honest, actually, I think having it disabled is actually slightly better. It actually makes a little bit more sense. But nevertheless, we will fix it because that's the way the game came. Okay, so that's working fine. So now we're going to go ahead and tweak this section of code here to see if we can actually make this work a little bit better. So we're going to go ahead and grab the pieces of code that we actually need from where we were before. Pixel shaders and disable is this guy. Yes. Okay, so I'm going to go ahead and snag this constants like we had before. And we're going to, I'm just going to go ahead and tweak this up to make it work with the Helix mod shaders instead. And I'll explain a little bit more detail how this is working like later on. So now we're going to need a new sampler here. This is the 2D sampler for S14, and this is Helix's sampler. Now this particular chunk here, this S14 is a different sampler. We can't interfere with these because they're actually used. S14, I've defined it in the dx9 settings.ini file as being the default sampler that's going to come in to pixel shaders. So nothing too significant about that. We just have to make sure all that stuff lines up. Okay, so S14 is going to be the sampler here. Now down here, the S1 was the one that was actually being used, but that didn't actually work, so we're not going to use S1, we're going to use S14. So now rather than do all that code there, I'm going to go ahead and make a second copy of that, and I'm going to comment out this block as being the original code. And then this is the one that we're going to modify and do what we want with it instead of what they want with it. So right now I'm going to go ahead and use c200.y as our parameter for turning on and off the particular thing there. So I'm going to make that a 1 to be Boolean true for we want this to be enabled. We want to actually enable our fix. So that's going to put it into R0, which is used later, and that's the reason I'm going to go ahead and keep this, is because R0 is used later to decide what to do with these things later down. We fooled with that a little bit before, but we need to make sure that that guy gets set. Okay, so now I'm going to go ahead and outdent this so that it's clear that it's our code, not their code. Okay, so since R0 is actually being used there, we can change this code to be R0 instead, since it's the correct value, rather than use the constant. We can't change a constant, of course, so we have to change that to actually be using this. Okay, so now I'm going to change this to C200. I'm going to make it Z. That extra parameters are not actually necessary. Make this S14 as our helix sampler. And then the rest of the code should be the same because nothing changes. The input vertex is XYW from what the vertex shader created. And then these parameters, we'll talk about those in depth in just a few minutes. These are all used as part of the operation. So this is the 3 lines of code. Should work to make it actually fix the shader effect. So let's give that a try. Save the file. Everything seems fine. Going back to the game. Back in 3D if everything works correctly. Okay, we are back in 3D. Missing our... Here, let me try something else there. Too many keys overriding everybody else. Okay, so we're back in the game. Should be okay. Now I'm pressing F10 to reload our new shader. And there you go. What about that? That is actually fixed. Hallelujah, we've made our first actual genuine fix of a shader effect, and it actually works correctly in 3D. Now, of course, we didn't actually do any work on that. The code was already there. We just had to make the code actually work. But nevertheless, that's still quite an advance. Okay, so I hope that's interesting for you. It took me 2 hours to figure out how to get that thing to work, so I hope you appreciate it. Okay, so go ahead and switch back out of the ball now so that we've actually seen the code actually functioning. Okay, so now we know that this little sequence of code here actually not only disables the effect, but this actually fixes the lava layer. Okay, so that's the just a brief intro as far as that goes. And so now you can actually see how these sorts of fixes are actually applied. It's coming in and fixing the vertex by actually doing a stereoscopic fix on it using the prime directive. So now let's go ahead and move back on to the next section, which will be how does this all work? Now that we've seen how the prime directive is applied within a shader to actually fix the effect at the pixel shader level, let's go ahead and dig into the guts of the prime directive a little bit to get a better background for how it all works. And this can give you some better background for how to find the right spot within a particular shader in order to fix things. Now, the best background for how the 3D works is a presentation that NVIDIA made, which is this NVIDIA content, and this is a pretty good presentation as far as that goes. It's definitely worth reading the entire thing in order to understand like everything there is to know about stereoscopic 3D, and I would recommend reading through the entire thing. Not all of it's going to make sense. Read it multiple times. As you learn more, come back and read it some more, and you'll actually get a better idea for what's going on. Now, rather than do that in the web browser, though, I'm going to go ahead and do it in the actual Adobe Reader instead, because it makes it a little bit easier to read and the layout is a little bit better. Okay, so we're going to go ahead and just look through a few pieces of this, a few of the slides. We're not going to go through the entire thing. And we're also not going to go into super depth as far as how the actual formulas work and how all of the pieces work. We just want to get a basic idea for what the parameters mean and what they actually can do. So, for example, what does the x mean within a parameter like v1.xyz, and why do we use x instead of z? That's the kind of thing that we're going to look at right now. Okay. This is a pretty good presentation. So 3D versus stereo, I think we pretty much all know about that. If you're in this class, I'm pretty sure you know about stereo. Interesting stereoscope basics, left and right shuttering, doing alternate eyes. Interesting little tidbit there, that left eye and right eye view there. If you do cross-eyed viewing, or rather parallel viewing on that, it actually is a 3D image. So the basic principle, we all know how it all works. I think there's no ambiguity there. And then there's 3D Vision Pro and some extra information about that. Now, we're not going to look at the OpenGL code or any of that. but we are going to look at this section here. So this is a presentation from how NVIDIA believes that stereoscopic should be created. And since we're using NVIDIA technology, we're going to look at this primarily to get their terminology so that we're all talking the same language. Okay, so in mono, essentially the people with only one eye are looking at a regular screen. This is how actually they're going to present the scene. So this is a 3D scene that's inside the computer. We're not going to worry about frustrums and all this other stuff. But the viewport is essentially what you're actually looking at. That's your screen. Now, one key thing here that is interesting is that the way that they present it is, see the coordinate axes here. So the X is going horizontally, Y is up, and Z is into the screen. So that's significant because that's how the stereo is going to work. Okay, so switching to the stereo mode, we have same basic structure, and now we have a left eye and a right eye. And it's notable that the left eye is offset from the mono eye to the left, and its right eye is offset to the right instead. So rather than just move one eye, they actually move on both sides of the regular mono eye. That actually matters in the formula because we're actually doing a plus and minus on the actual values. Okay, continuing along. So shifting along the mono axis there, eye directions are all parallel. They don't vary in. There's our virtual screen. Now we throw in the frustrums, which are essentially what each eye can actually see in terms of the angle, where it actually intersects with the physical screen and what you'll actually see. So those are important for some sort of later things, but right now it doesn't really matter that much. Okay. Then we have two images that are generated from the virtual screen. We have our actual, real screens that are actually made here, the left image and the right image, and that's why they overlap and cause all the fuzzy effect that you actually see. Okay, that's what it looks like when they're doubled up. The right image is here, the left image is there. They overlap, and I'm sure you've all seen that without your glasses on. Okay, so that's the basic principle. No big thing there. The most thing to note is that the left eye is shifted to the left and the right eye is shifted to the right, and the coordinate axes. Okay, I'm going to go ahead and keep going forward. Now this section here, defining the stereo projection, so this is significant from the standpoint of language as well. So now we've changed the coordinate, so now we're actually looking at a top-down view instead. So now X is up and down in the picture here, but it's essentially left and right when we're actually looking at the screen, if you get the idea. Y is coming straight out of the screen toward us, and Z is going into the screen. Okay, so same thing is for left eye shift and right eye shift, it's actually minus X to get to the left eye and plus X to get to the right eye. So same idea with the frustrums and showing it. They make a big deal about not towing it in. If they, some people actually make this mistake. I think TriDef has something like that where they tow it in and it's actually not the right thing. The lines are all parallel. This is the interaxial distance between your two eyes. You probably know about the interaxial distance. And this is one of their formulas that they use, and that's why screen width actually matters, is because the separation value, so the actual separation that we dial up with our emitters, is actually defined to be the interaxial distance divided by the screen width. So these are not arbitrary numbers essentially, but we don't necessarily actually care about the formula, but it's interesting to see how the pieces hook together from a math standpoint. This is how NVIDIA defines it. There are other ways to do it, of course. Okay, convergence is another thing that we run across periodically. And convergence is the screen's depth in the eye space, what they call eye space. I'm not going to go into that also. And they defined it as being where the frustrums intersect, and that's where the virtual screen actually appears to be. So convergence can actually be dialed the way that we do it with our advanced settings, and actually draw the virtual screen out of the wall, out of the monitor, into the room instead. Parallax is the essentially the piece that tells you how deep something shows up in the screen. So for example, if the vertices are widely separated, then they'll actually seem like they're further into the screen. If they're not separated very much, they won't seem like they're very separated at all. So it's parallax is the way that we actually determine whether something's in 3D or not. Okay, and then this is the discussion about depth perception and how it actually works using their sort of mechanism. So it's actually perceived as the real screen naturally, in and out of the screen versus using the convergence. Then they get into parallax using the normalized image space and parallax and separation. This part of the curve here is actually separation. This is inside the screen. This is outside the screen. And the convergence allows you to change this point to wherever you want it to be, depending on how much you want to have outside of the screen, how much you want to have inside the screen. And it's notable that we can go a lot further into the screen than we come outside of the screen because of the way your eyes work. And interocular distance is about 6.5 centimeters, and that's considered maximum available parallax. So anything that's at the maximum parallax will look like it's at infinity to our depth perception. Okay. Moving along, and then this is why we don't want to have that be any wider than that, because if you do, then your eyes have to diverge, and that causes problems with your eyes. Some of us who have done a lot of this actually have the ability to do a little bit of divergence without experiencing any sort of pain, but in general, it's not a good idea. Eye separation is maximum comfort that you can see. The same thing holds true actually for stuff coming out of the screen. It's not so much eye comfort there, but if it comes too far out of the screen, then it'll actually separate and you won't be able to make an image out of it. They go into a parallax range and parallax budget for how you can do it. Parallax budget is essentially how much a specific person, and it's specific to different people, how much they can see. So what's the difference for what's the closest thing that they can see versus the thing that they can see the farthest away. Some people have a much larger parallax range than others. When you first start, your parallax range is actually pretty small, and that actually grows as you get experience. So we're not going to go into the parallax budget, but this is all interesting stuff and gives you some idea of like how it goes. So now, interesting tidbit, convergence is intended by NVIDIA to be controlled by the application. Naturally, as enthusiasts, we much prefer to control it ourselves. But that's one of the reasons why it's under advanced, is because from NVIDIA's perspective, it's not supposed to be something the user changes. Okay, this is how you actually do rendering from a code standpoint. We're not going to look at that, but we are going to look at this. This is slide number 49, and this is, in fact, the prime directive. So this is how stereo projection is implemented. This is the formula that's used, and it's also called the stereo correction. And the basic principle is this formula here. And the I sign is decided +1 for right, -1 for left, just like we saw earlier, where it's incrementing or decrementing that value. So it actually adds in this chunk of the code here, or this chunk of the formula here, to decide whether it's going to move the image to the left or to the right. So that's it. That's the prime directive. The basic principle is that we're taking into account separation and convergence as part of the mechanism, and we use the W parameter, which is inverse of the Z. I'm not going to go into some of those other details for how the actual matrices and the math works, but the basic idea is that this you can think of this as being the Z parameter of the actual vertice that we're actually looking at, and we subtract convergence from it, multiply by the separation, and if it's the right eye, we would actually add that into the original position. If it's for the left eye, we actually subtract it. So it's a plus or a minus to move it out of the mono position into the stereo position. That's basically about it. We're not going to necessarily know exactly how all of this works, and I won't go into the background for how the math works because it's not interesting for our purposes. But this is the formula that we always apply when we're trying to actually do a stereo correction, like we saw at the first part of this lesson. Okay. Now, one thing to note is that the I sign here is actually automatically assigned by the driver. So we don't actually have to do this. We don't have to figure out the I sign. It's actually done for us automatically. So the only formula that we're actually going to use is this clip position I sign as we go. So that's what I'm actually showing here is the prime directive is this formula here. It's the same basic formula, but in our case we actually don't use the I sign, but we do the plus equals variant. So now, with that in mind, I'm going to go ahead and show you another thing that I've made here. This is a canonical stereo code. So this is translating the prime directive from straight math into actually what the code is going to be. And you can use this as a reference and look at this to see how it actually works. So I'm going to go ahead and go to the HLSL version because the code is more clear in high-level languages. So this is the actual mechanism that happens when we're actually doing the code. We load a stereo parameter. This is a sampler. It's just the way that NVIDIA has defined it, but we have to do this in order to be able to get access to these. So then the stereo parameter here is actually X and Y of that particular float 4 is actually going to be X is the separation and Y is the convergence. So those are the two parameters that we need. And so then when we would actually do a fix, we would actually do this formula here, which is taking the location W, essentially the Z parameter, subtract the convergence off of it, multiply the separation, and then plus equals is add whatever this value is back into the original location. So that'll give you a shift to the left for the left eye and a shift to the right for the right eye. It's going to add in a negative number if it's for the left eye, and it's a positive number for the right eye. So that's it. That's all there is to applying that formula. In assembly language, it's a little bit more complicated. In DX9 and Helix mod, this is the code that actually happens when we would do that. Basic principle here is we have our constant that's actually used. This magic number is actually applied using this texture load operation. So the C200Z is actually applied in there. And because of the way that the NVIDIA driver functions, that converts this sampler into, or actually figures out from the driver what the actual convergence and separation are at that moment in time. Puts it into R30. R30 gets to use those particular parameters. So same thing, R30.x is the separation, R30.y is the convergence. So in this case, we want to actually do W minus convergence parameter. So if R0 is our output position that it needs to be fixed, then we're going to add these two parameters together to get W minus convergence. So it's adding a negative number of the minus convergence, puts that into W back. So then we want to take this clause and multiply it by separation. So separation is R30.x, and we multiply that by what we just created there, the R30.w, and then we put that into R30.z as being the this clause here. Then we actually want to add that and put it back into the original R0.x. So we add in our R30.0 to the original R0.x to create the final R0.x, which means that it's fixed. And that's it. That's all the formula is actually doing. And then we apply that whenever we think that we need a stereo fix. Later on, we'll start looking into some specific examples of how to apply the stereo fix and how it actually works and where to apply it. Okay, so nothing more to say there, really. Without going into further depth on that, this is a slightly better version of it when we're more accustomed to actually the code. I recommend staying with this wordy version for a little bit until you get really used to it. Later on, you'll become so familiar with it anytime you see this constant that it'll actually remind you that this is probably going to be some sort of stereo correction. Okay. This version is slightly better because it's one instruction shorter, and these things run millions and millions of times because of the pixel shaders, so one instruction actually can make a fairly big difference on some of this stuff. This is the version that you'll see mostly in the Helix mods, where they separate out the multiply and they add into two separate instructions. But because of the way assembly language works, we can do multiply add at the same time. Okay, that's about it. That's all I really want to say about the prime directive and how the actual code works. As a last takeaway idea for this particular slide in the prime directive, I want to emphasize that the parameter that we're actually changing is the x parameter of any given vertice. Now it's a little counterintuitive. You might expect that we'd actually be changing the z as being sort of the depth in the screen, but that's the depth in the actual 3D model, not what we're actually seeing on the screen. What we're seeing on the screen is what they call the eye space or clip space, and in order to get the 3D to work, it's the x parameter that actually changes. So the reason that's significant significant is because any change that you make to a X parameter on a given effect within a game will actually change the depth that you perceive in the game. So if you increase the in the X difference, then it'll actually look like it goes deeper into the screen. If you decrease the distance, it'll actually seem to come out to the screen. And if you set the X to 0, then that will actually be at screen depth. And when X becomes negative, then it inverts and it actually comes out of the screen as a pop-out effect. So we're going to use that over and over and over again as we fix things and try to decide like what we're actually going to do. So keep that in mind, that we're changing X, and that making it larger tends to make it go into the screen until you get to the maximum size, and making it smaller actually brings it out closer to us, reduces its depth. Please take a look at the rest of this particular presentation. There's all kinds of interesting stuff in there. It gives you some idea of like how the automatic mode works and some of the possible like glitches that actually like happen as far as that goes. Okay. Now that we've taken a look at the fundamental stereo correction formula, the so-called prime directive, we can see now how to apply it in different shaders to actually fix stereo effects. In general, we aren't going to worry about the actual formula itself. We're just going to take those 3 lines of code and paste them in when we need to actually fix a shader. But I think that the background actually gives you a better idea for what to look for inside of a shader while you're doing experimentation, and possible good spots to actually plug in that formula. So along that lines, what I'm going to do is I'm going to show you how to fix the lava effect, but using a vertex shader this time instead of the pixel shader. Now this is a vertex shader associated with the same effect, and we're going to fix that text coordinate 5, but we're doing it earlier in the pipeline just to see how it goes. You may or may not understand this exact part, but I wanted to give you a demonstration of how you can fix the effect in a different spot in the pipeline. Now in general, we can fix the effects either in the vertex shader or the pixel shader, but there's definitely different choices that are better depending upon what you're trying to fix. If we're trying to fix location problems, locations are almost always vertex problems, location problems. So like a skybox that's being too close or wanting to move the HUD into a different spot, that would be a vertex shader thing, because that's a position orientated type of problem. Now if we want to make the HUD a little bit more transparent, that would actually be a pixel shader, because the transparency effects are applied in pixel shader typically. And some very complicated effects like shadows and water and fire typically are done in pixel shaders using deferred rendering, which is a future class we will talk about. Okay, so let's go ahead and just take a look. We're going to run the ball and look at the lava level. I'm going to show you a different one this time just for interesting sake, and we're going to hunt down the vertex shader. Okay, here we are in the ball. We're actually taking a look at the bomb room. The bomb is over there in the elevator sort of area. And this pool here is actually a pool of oil. I'm going to show you this. I'm going to go ahead and re-enable that effect so you can actually see how it looks. You can see the haloing around the gun and the double imaging there. So the reason that that is significant is because that's going to be the quiz, is to see whether or not you can apply the same effect that we're going to do here on the lava, where it's busted over here, as you can see, to the effect here. I believe these shaders are nearly identical. So that'll be interesting. Now I'm going to go ahead and disable that effect, and you can see that it fixes that. Okay, so I'm going to go ahead and unfix the lava effect so that it's more clear when we actually get results when we're working. So back in the code, this is the lava effect in the bomb room. This is the pixel shader. And the pixel shader has already been tweaked in order to fix that one layer, and that was what we did in the last lesson. So rather than leave that on, I'm going to go ahead and comment out all of the code that we had in there before that was actually doing the toggle for making it turn on and off our disabling layer, and so now the code is actually back to the way it was originally, which means that it's broken. Okay, so I'm going to go ahead and switch back in, and we should get F10, and you can see that it's quite broken over there on the lava. And now when I hit the M key, I can see that it changes the oil, but we don't have any effect on the lava. So we succeeded in putting it back to the original code. Okay. So we got the lava over here. It definitely is broken. Now let's go ahead and do some shader hunting and try and find the vertex shader now that this is just back to working the way it was normally. Okay, so I'm going to do the normal thing. I'm going to step backwards. 46 shaders in the list. We're just going to hold it down and see if there's anything that stands out. First pass around anything that seems like the right candidate. All right, that was a full cycle there, and I would say nothing really stands out as being a particularly great candidate because we didn't get just the lava layer. We got like the entire room dark. We get some other effects that seem interesting but are different. This one is maybe interesting because we have a little bit of fountain going on there, and we still have fire going over there. So that one's a pretty good candidate. Keep going backwards. Some ambient occlusion. Definitely not the fountain itself, because the layer actually did go. Full dark is rarely the right case. That's usually some sort of a full screen effect. That one, not very likely. Some sort of shimmering thing. Walls. More blackness. And we've wrapped back around. Okay, so given the candidates that we've got, I would say that the only one that even is remotely reasonable is this one, which is 4A65B800. And we're going to go ahead and take a look at that shader. I'm going to go ahead and save that off. Okay, switching back out. Now we're going to go ahead and go to the shader folder. So let's see, we are in Win32, dumps, single shaders, vertex shader. Here's 4A65B800. So this is the shader that we just dumped, and this is our candidate for doing lava from the vertex shader standpoint. So it is a vertex shader. It's also notable that we do not have the NVIDIA stereo correction fixes in this thing. No constants in here to like turn it on and off, and no if statement in here to do that particular effect. There is an if statement, but that's for some purpose, not for the NVIDIA stereo correction. Okay, so now the things to note here for the output. We have a position as output 5, and text coordinate 5 is 03 instead. And this little signature here actually matches what is in our pixel shader of 4, 5, and 6. So here's our pixel shader that we were just putting back to normal. And you can see that 4, 5, and 6 are actually like used here as well. And so that's a very likely candidate that we have a match. Okay. So given that we have a likely match there, we would go ahead and do the save as this into the shader override folder. But of course, I've already done that in advance, so we're going to go ahead and go back here. This is actually already ready live, so we can just go ahead and edit it straight up without having to relaunch and do some other stuff. So this is, in theory, this is the lava effect in the bomb room. Vertex shader, okay. So now this code is actually live, so we can go ahead and edit it and do what we want to it in order to like make it fixed. So making sure we got the right one, yes, 4, 5, and 6, and position is there. So output 3 is the most likely candidate, so let's go ahead and just double check to make sure that that's actually the right answer. And we can see that output 5 is the actual location, which is being assigned by R4. Now, R4 is calculated further up by whatever mechanism that they decide, but in any case, it definitely is the output for the location, and it's being assigned to this texture as well. So it's fairly likely that this is the right spot, but the way that we can tell is by going ahead and commenting that out. Now, we'll go back into the game and see if that actually affects the shader. All right, we're back in. Now, if I hit F10, and there you go, look at that. So the we can disable that layer the same way as we did in the pixel shader, and we actually have found the right spot and the right shader, and it's loaded, and everything is working correctly. So we're actually in pretty good shape there. Okay, so clearly this is in fact actually the same input that this one is getting by the V1. That is the V1 from the pixel shader standpoint now instead. And it's coming from here, and we have to stereo correct this one. Later on we'll go into why this is the actual one. I'm just going to sort of show you right now how we actually do the actual technique as opposed to explaining why we'd actually choose this particular spot. Okay, so this one is clearly the right spot, so now we're going to go ahead and add our shader fixing code to this spot in order to try to fix the effect instead of disabling it. This is just disabled right now, perfectly acceptable, but let's go ahead and fix it instead. So I'm going to go back into our page here, which is our canonical stereo code. You can find it here on the web page. These are multiple versions of it that are slightly better depending upon what version that you're actually going to use. We're going to use the wordy version right now. because we're learning, and so having it be wordy is actually helpful right now. Later on, maybe we don't care as much, but right now it definitely is helpful to have it be extra comments. Okay, so I'm going to plug in this declaration for the shader, and I think that's out of order. I'm going to go ahead and do it this way. So no samplers are actually being used in this vertex shader right now, so we can use S0. I guess that's right. Okay. And we've got our constant that we're going to use with the 0625 magic number. Okay. Then down here at the bottom, we're going to go ahead and plug in the code here. And this code is going to be after everything happens. We've disabled this output line here, so now we're going to re-enable that output line down here at the bottom. So at the bottom, we're actually going to put in the move statement that would have actually been there, but we're going to use R0 because R0 is the sequence that's actually used here for actually doing the fixing. And so that's why I leave these comments here, like at this point R0 is expected to be the output position placed, but without stereo. So since R0 is there, we're going to assign it to the output of 03. Okay, now since it's not assigned correctly at the moment, we need to actually put that into R0, and we know that it's R4 because that's where it would have normally gotten it from. So we're actually going to put it into R0. We're going to futz around with R0 to actually do the stereo correction, doing the stereo correction code. Then we're going to take that fixed location and put it into 03, which in theory should move that texture into the right location and fix the effect. Okay, so that's basically all you do as far as actually doing an effect. That's the actual mechanics of doing it is pasting in the sampler and the constants at the top in the declaration section, then pasting in the code that actually does the fix and make it line up with whatever the output is actually supposed to be. So it's not more complicated than that. Those are the actual mechanics of doing the fix. Okay, I'm going to go ahead and save. We're going to switch back to the ball and take a look-see on whether this works. And here goes F10. And there you go. What about that? So we actually have fixed the shader effect. You can see the edge of the lava is actually doing that flowing effect now again, like it did before. Let's see if I can jump on this thing here. Nope, I can't quite do it. So it's not totally clear there. You can actually see a little bit better. So the flowing effect on the edge there. So we've actually fixed the effect, not just disabled it. How about that? Okay. So that's all I want to show you for the time being here. We're going to go ahead and switch back out and make sure that we've finished that section. So we've edited the shader, added our stereo correction. It all works. How about that?